Hello. I'm going to talk about real analytic singular Radon transforms with product kernels, necessity of the Stein-Street condition. I will first talk about what the operator is, and then give some concrete examples as motivation. After that, I will give a necessary and sufficient condition for the operator boundedness. And because that condition will be a bit abstract, I would also like to illustrate that condition in the translation-invariant polynomial case and Heisenberg group case. At last, I will talk about general real analytic case, which uses Carnot-Carathéodory geometry. Okay, this is the operator. When t acts on f, it's equal to a smooth bump function psi times integration of f of the function gamma and integrated against k, kernel k. Here, psi localizes the operator. And here, kernel k is assumed to be a product kernel on Rn, which I will define in the next page, and assume it is with compact support. We also assume that the function gamma is real analytic and it maps from neighborhood of the origin in R capital N cross R little n into R little n. And we assume when t equal to 0, this is identity map. Okay, so such operators are called singular Radon transforms. For the product kernels, if it's one parameter, it is simply the Carnot-Zygmunt kernel. For more parameters, say 2 parameter, if we are given a decomposition of Rn into Rn1 cross Rn2, then a product kernel KST relative to that decomposition is a distribution of Rn, which satisfies the following differential inequalities and certain cancellation conditions. That cancellation condition can be too technical to state here, but the cancellation condition for the Carnot-Zygmunt kernel is well known. And the cancellation condition here is defined inductively on the number of parameters. Okay, so that's singular Radon transforms with product kernels. So let me give you some concrete examples. So the study of singular Radon transform started in 1966 when Fabs proved that Hilbert transform along parabola is bounded on every LP. And the kernel 1 over T can be replaced by any Carnot-Zygmunt kernel on the real line. The next example is about operator, is about Hilbert transform along vector field V on R2. And it is proved by Bourgain, Street, and Stein that for every real, that if the vector field V is real analytic, then the operator T is bounded for some epsilon and for every LP. And this 1 over T kernel can be replaced by any Carnot-Zygmunt kernel with sufficiently small support. It is also conjectured by Stein that we only require the vector field V to be Lipschitz in order to make the operator T to be bounded for some epsilon. And that conjecture is still remains open. So in these first 2 examples, I gave operators with Carnot-Zygmunt kernels, which means it's a 1 parameter case. And that in the next 2 examples, I'm gonna give you some 2 parameter cases. So in this example by Nagel and Wainger, inside F we have x plus st, and we have kernel 1 over st, and this is unbounded for every LP. But if we change that operator slightly by adding s squared plus t squared here, then the operator becomes bounded on every LP. And this kernel 1 over st can be replaced by product of any Carnot-Zygmunt kernels, or more generally can be replaced by any product kernels. Okay, in summary, we have seen that in the first 2 examples, both are with Carnot-Zygmunt kernel and both are bounded. And in the later 2 examples, we have seen that if the product kernel is with more than one parameter, then the operator T may or may not be bounded on LP. So the question is, can we exactly characterize when T is bounded? The answer is yes. So let me formulate that. So again, this is the operator T, and for simplicity, we consider two-parameter case with S, T, and the goal is to find a necessary and sufficient condition on the real analytic function gamma, such that T are bounded on LP for all product kernels K, for all smooth bound function psi, and for all P strictly between 1 and infinity. It turns out that with that same condition, which I will talk about in a minute, it is also necessary and sufficient that even if I replace here for all P by for some P. Okay, let me give you a brief history. In 1999, Chris, Nagel, and Wainger studied such operators with Carnot-Zygmunt kernel and with smooth gamma. Later in 2011, Stein-Street gave a sufficient condition for such operators to be bounded for all kernels with sufficient small support, and they are with smooth gamma. And what I did is to prove that Stein-Street condition is also necessary if we assume gamma is real analytic. Okay, before I start stating that necessary and sufficient condition, let me first introduce some notions. So for simplicity, let's assume the function gamma can be written in this exponential form, where the exponential form is defined using the ODE flow. So in the exponent, it is a polynomial of S and T with coefficients being vector fields x sub alpha beta, which are defined in a neighborhood of 0 in Rn. And suppose exactly one of the index alpha beta is non-zero, then we say x sub alpha beta is a pure vector field. If both of alpha beta are non-zero, then we say it is a non-pure vector field. Okay, so before I state the more abstract necessary and sufficient condition, let me first give you a necessary condition, which is that every non-pure vector field is spanned by iterated commutators of pure vector fields with bounded coefficients on a neighborhood of 0. Okay, so again, this is the operator T and this is the function gamma, and they gave rise to vector fields x sub alpha beta. So to make the necessary condition I just talked about also sufficient, we need a scale invariant version. So let delta to be in 0, 1 squared, and we dilate x sub alpha beta by delta 1 to the alpha, delta 2 to the beta. In this way, we obtain dilated pure vector fields and dilated non-pure vector fields. Now, the necessary sufficient condition is that every dilated non-pure vector field is spanned by iterated commutators of dilated pure vector fields in a uniform way, uniform in delta. The exact meaning of that uniformity is too technical to state here. It uses Carnot-Carathéodory geometry, but I will talk about it a little bit at the end of the talk. Okay, now I want to give an example to explain what these conditions mean. So it's an example by Nagel and Wainger where gamma is equal to x plus st. When written in the form of exponential form, the exponent is equal to st multiply the vector field dx. So we have no pure vector fields. We have one non-pure vector field dx. So the non-pure vector field is not spanned by pure vector fields. So it does not even satisfy the necessary condition we talked about earlier, not to say the necessary and sufficient condition. So by our theorem, the operator should be unbounded for some kernel K. And indeed, we can prove that we can find such kernel K to make operator T unbounded. I'm gonna give you a short proof sketch. So the key is to find such kernel. So let kernel K to be the summation over J of the smooth bump functions sigma dilated by 2 to J and 2 to negative J. And we suppose this smooth bump function satisfy the cancellation conditions that when integrating along S is zero function, when integrating along T is also zero function. And in addition, we require that when sigma integrated against ST, it's non-zero. Okay, let's see. Now our function TFX becomes inside F is X plus ST, and it's now this sigma over J is summation over J of sigma divided by 2 to J to the negative J is our kernel. Now, if we make a change of variable, we let 2 to the JS to be our new S, and 2 to negative JT to be our new T. Then it will result in the ST in the front be dilated by 2 to J times 2 to negative J, which is 1. So now our function becomes the infinite sum of the same term. And this condition that sigma integrate against ST to be non-zero guarantees that the single term is not a zero operator. So we have an infinite sum of the same non-zero operator. So it's unbounded, it's blow up. So I have proved for this case, X plus ST is unbounded. And now I'm going to give you more examples in the translation-invariant polynomial case, because in this simple case, our abstract necessary and sufficient condition can be expressed in terms of Newton diagram. Okay, so again, this is operator T, and delta is in 0, 1 squared. And example 3 we have just talked about is unbounded. And example 4, let gamma to be X plus S squared plus T squared plus ST. And now the dilated pure vector fields are delta 1 squared dx, delta 2 squared dx. And non-pure vector fields are delta 1, delta 2 dx. And we don't need to worry about iterated commutators, because in this translation-invariant R1 polynomial case, every commutator vanishes. And now, by a simple calculation, this delta 1, delta 2 dx can be written as a linear combination of delta 1 squared dx and delta 2 squared dx with bounded coefficients. So by our theorem, our T should be bounded for all kernels. And next example, we change gamma slightly by raising the power S and T to the 3. And so the pure vector field becomes delta 1 cubed dx and delta 2 cubed dx. And now, by a simple calculation, we can show that this delta 1, delta 2 dx cannot be written as a linear combination of delta 1 cubed dx, delta 2 cubed dx with bounded coefficients. And so by our theorem, the operator T is not bounded for all kernels. Okay, I have illustrated how we use our theorem. And next, we can see a pattern from it. So in example 4, the red point, which denote the non-pure power, lies on or above the line connecting the two smallest pure powers on the two axes. And so it's bounded. And for example 3 and example 5, the non-pure point does not lie on or above the line connecting the two smallest pure powers on the two axes. So it's unbounded. So in other words, the necessary sufficient condition in this translation-invariant R1 polynomial case is that every non-pure power lies in the Newton polygon generated by pure powers. Okay, so I would also like to give a short proof sketch to prove why example 5 is also unbounded. So the idea is that to reduce the mildly bad situation in example 5 into extremely bad situation in example 3 to prove it's unbounded. So we start by supposing by contradiction that the operator T are bounded for all kernels, and it does not require much effort to prove the following family of operators are uniformly bounded. So this is our gamma x plus s squared plus t squared plus st, and we choose our kernels k sub delta naught to be summation over j and delta naught to -2, where delta naught is a number between 0 and 1. Multiply the smooth bump function sigma, first dilated by 1 over delta naught, and then dilated by 2 to the j and 2 to the -j. Okay, and then it's not too hard to prove that if we conjugate these family operators T delta naught by dilations, they are still uniformly bounded. So this phi delta naught denotes dilation on R, and phi star denotes pullback. Okay, now the conjugated dilation of T delta naught is equal to this. So F is dilated by delta naught to the -2, and X is dilated by delta naught squared. And this is our kernel just chosen. Now, by a change of variable, we let S over delta naught to be the new S, and T over delta naught to be the new T. And then simplify things, the operator becomes this. So now let delta naught goes to 0. The limit operator is exactly the operator in example 3, which should be unbounded. But we just said that these families of operators are uniformly bounded. So their limit operator should also be bounded, which is a contradiction. Okay, so we have finished proof that the operator in example 5 are bounded for some kernel. So we have just to deal with a very simple case. So let's look at Heisenberg group case, which is still very simple, but slightly more complicated than the previous case, because it has half commutators, but only with first order commutators. So Heisenberg group case is a Lie group whose all the left invariant vector fields are a linear combination of these basis vector fields x, y, t with constant coefficients. And this x, y, t need to satisfy following relation, that the commutator of x, y is equal to t, and commutator of xt and commutator of yt are both 0. So this means that every point on the Heisenberg group can be written in this exponential form, with exponent being a linear combination of x, y, t with constant coefficient, and with basis point, the origin. So we actually can realize this x, y, t satisfying the above relation with dx, dy, dt being the standard coordinates of R3, we can let x to be dx minus half y dt, y to be dy plus half x dt, and t to be dt. Okay, so that's a Heisenberg group. And let's consider example 6 here. We let gamma in the exponent, let it to be sx plus ty plus stt. Now the dilated pure vector fields are delta 1x and delta 2y. and their commutators are delta 1, delta 2 t. Recall that in the previous translation-invariant polynomial case, all commutators vanish, so we don't need to compute their commutators. But here, it has a first-order commutator, but fortunately, it doesn't have higher-order commutators. Higher-order commutators vanish. And now the dilated non-pure vector fields is delta 1, delta 2 t. So it is spanned by pure vector fields, dilated pure vector fields with boundary coefficients uniformly in delta. So it satisfies our condition. So by our theorem, T is bounded for all kernels. And next example, we change gamma slightly by making the coefficient of y to be t squared, coefficient of t to be s squared t. And now the dilated vector fields becomes delta 1x and delta 2 squared y. And their commutators are delta 1, delta 2 squared t. Okay, now, but the dilated non-pure vector field is delta 1 squared, delta 2 t. And by simple calculation, this is not spanned. It cannot be written as linear combination of the dilated pure vector fields together with their commutator with bounded coefficients. And so by our theorem, T is not bounded for all kernels. Okay, so we have illustrated how we use our theorem in this Heisenberg group case, and now we can see some pattern in the pictures. So in the picture on the left-hand side, we can see the red point, the non-pure power vector field T. And let's draw an arbitrary line passing through that point. And we require that line to intersect xy axis at the positive half of axis. Okay, and now with the red point and with any line through it, and let's look at the pure vector fields together with their commutators that lies below that line. So which include here x, y, and t. And so they span our non-pure vector field T. So it is bounded. But for the picture on the right-hand side, the non-pure vector field T with power 2, 1, and let's look at the dashed line through it. The only pure vector field together with their commutators that lies below the dashed line are x and y, which do not span T, the non-pure vector fields. So the operator is unbounded. Yeah, so the necessary and sufficient condition in this case is the following. For any non-pure power and any line through it, the pure vector fields and their commutators that lies below the line should span the non-pure vector field. Okay, so we have talked about two very simple special cases. And what about the general real analytic case? And how do we use the fact that it's real analytic? So let's see. So in the translation-invariant case, polynomial case, every commutator vanish. And in the Heisenberg group case, we only have first-order commutators, high-order commutators vanish. The corresponding property of real analytic case is called Noetherian property. So that is for any arbitrary set of real analytic vector fields, it is a finitely generated say infinity module. And that is a key property that we use about real analyticity. Okay, next I'm going to talk about Carnot-Carathéodory geometry, which I have mentioned in the beginning. So let's recall how we prove example 5. We reduce example 5 to example 3 by construct dilation phi sub delta naught squared. And in fact, unlike in this very concrete example, we have gamma equal to x plus s cubed plus t cubed plus st. In general, we have to decide for every possible case how to find appropriate dilation to make the following reduction process work. And more complicatedly, in the general real analytic case, the global dilations does not work anymore. So we have to carefully design local diffeomorphism for every possible situation to make this reduction process happen. Okay, so that's why we introduce this Carnot-Carathéodory geometry, because with that geometry, I can see clearly what each possible situation needs, and thus cook up a local diffeomorphism accordingly. Okay, so let's define this Carnot-Carathéodory geometry. So given a finitely many vector fields, x1 through xq, define an open set omega. And each vector field is associated with a 2-parameter multi-index, alpha1 beta 1 through alpha q beta q. And let the center of the ball to be in omega, to be in the domain omega, and let the radius delta to be 2-dimensional. And the Carnot-Carathéodory ball with center x radius delta is defined as the set consists of every point y in the domain omega, which can travel, starts from x within unit time with velocity spanned by this dilated vector fields. And the coefficients under certain norm should be bounded by 1. Okay, with this definition, notice that if x1 through xq does not always span Rn, then the ball, the Carnot-Carathéodory ball Bx delta does not necessarily always have full dimension. So when in the proof for the general analytic case, we have to deal with situations like for some point that in every neighborhood of that point, the dimension of the spanned by these vector fields, and that's the dimension of the Carnot-Carathéodory ball, is not constant. It's not constant at any neighborhood of that point. Yeah, so to deal with that complicated situations, I will introduce the next theorem about this Carnot-Carathéodory geometry, which covers such complicated situations. So which holds even when the dimension of these vector fields, the dimension of the ball varies. So let me first remind you of the classical theorem of Frobenius. So given smooth vector fields x1 through xq on Rn, or more generally on domain on open set on Rn, and suppose it satisfies the involutive condition, that is, any commutator will still spanned by x1 through xq, then we have that through every point x, there exists a unique manifold whose tangent spaces are always spanned by x1 through xq. So in other words, we can say that if vector field satisfying this involutive condition, then we can foliate the domain into leaves. So that's qualitative for Frobenius, and that's and what I want to introduce to you is the quantitative for Frobenius, which is by Street in 2011. And roughly speaking, if our vector field satisfying the involutive condition uniformly, then for every point x in the domain and for every delta with 2 dimensions, and there exists a corresponding local diffeomorphism such that the Carnot-Carathéodory ball with center x radius delta is comparable to the image under this local diffeomorphism of the Euclidean unit ball with the same dimension as the Carnot-Carathéodory ball. And with this local diffeomorphism satisfies certain quantitative conditions. Okay, so recall this is the reduction process when we prove example 5 is unbounded. And comparing to this very special case, in the general case, one difficulty lies in that the reduction process might need to be implemented more than once. And we not only we need to choose the ratio delta for this local diffeomorphism phi, but also we need to choose a center to implement such reduction process, because a general case is non-translation invariant. Okay, so that's all. Thank you for your time.